Honors Algebra 2, Chapter 14, Section 3. This is Part 2 of Day 2 of Part of Section 3. More on the identities and how we're going to solve and simplify trig identities. And so these are the ones we got to know for trig identities that we're going to talk about in this section. Reciprocal identities we already talked about. Those you should feel pretty confident about. Tangent and cotangent identities. Again, these we've already been discussing how tangent, sine, or cosine. You should feel comfortable with those. We mentioned about Pythagorean identities in the last video. They're a little more complicated for students at first, especially the tangent and cotangent ones, but these are ones you need to be able to be comfortable with and know. The next two we've not discussed yet, the cofunction identities, where sine of pi halves minus theta is equal to cosine. And that comes from where if I look at a triangle, a right triangle, so the other two angles here have to become 90 degrees. So they equal the pi halves. And so the sine of this angle here is going to equal the cosine of here because they're both talking about this side here, x over r. Cosine would be the adjacent over r, sine of this one would be the opposite over r. So those would be equivalent ratios. So the sine and cosine there would be equal. Looking at complementary angles, how the sine and cosine actually have equivalent values for complementary angles. The negative angle identities, this goes back to our inverse functions, and we're looking at how we have some repeat ratios sometimes and looking at the sine. So if we have a negative angle in the opposite direction, we can get a coterminal angle. The sine of the negative theta is equal to the negative sine of that theta. And then cosine of negative theta is equal to cosine of that positive theta, and tangent negative theta is equal to negative tangent theta. And so these are trig identities we get to use within problems. And so being able to verify. These are a little easier, I feel, than for students, verifying compared to simplifying. Simplifying, you don't know where you're ending. Verifying, you do. We know we have to have the left side here equal the right. We can start on whichever side we wish, but we have to stay on one side. So if I want to start manipulating the left-hand side, I have to only manipulate the left-hand side and keep the right-hand side the same, sine squared theta. You can choose which side to manipulate, but you need to stay on one side. So I would probably choose this left-hand side because there's more operations that are occurring here, so I see more of the trig identities. And so like secant squared theta minus 1, that's something I have an idea what that is. And if you don't need to pull up your trig identities here, here's our secant squared theta. But it's not the same one, but I can manipulate this. If I subtract 1 to both sides, then I get tangent squared theta is going to equal secant squared theta minus 1. So now I see secant squared theta minus 1 is equal to tangent squared theta. So then this numerator here is actually equal to tangent squared theta. Still divided by secant squared theta. This whole thing still equals the sine squared theta. So now I need to manipulate them more. Now, tangent squared theta is actually rewritten as the sine squared theta divided by cosine squared theta. And we're dividing by secant squared. That's the, actually I'll write that out here, dividing by secant squared theta, which is 1 over cosine squared theta. So I was going to do more than one step there, but it's a verifying identity. I have to make sure that my steps I write down it is written in a way that the readers can follow the roadmap or the path to show equivalency. And so now that I have this written down in division, I can change my division to multiplication. So sine squared theta over cosine squared theta times the reciprocal, cosine squared theta over 1. So now these cosines are going to reduce out, so I get sine squared theta is equal to sine squared theta. And we have our equivalency there. So we manipulated the left-hand side to show how they both equal sine squared theta. Here's a second one. So we have secant x plus tangent x equals cosine x over 1 minus sine x. So there's a few algebraic concepts that pop up within verifying. For instance, on the left-hand side, we're adding we're adding two functions. On the right hand side, we're just dividing. So the left hand side, if I wanted to deal with that, I would want to add these, and to add these I would have to change them so they have fractions, so we find some common denominators to add. On the right hand side, we have a division where our denominator is a binomial 1 minus sine x. So there's also an algebraic concept here that we talked about in previous class, that we can multiply by the complex conjugate, sometimes it's called, or the difference of perfect squares, the binomial that allows us, when we FOIL it, to get our squared terms. And we'll see that, but most of you would start on the left hand side here, so I'll continue that. The secant here be 1 over the cosine x plus tangent, which is sine x over cosine x. And then the right hand side is doing the same. So the left hand side we can add that because it already has common denominators with 1 plus the sine x over cosine x equals cosine x over 1 minus sine x. Now, at this point, some students want to cross multiply. We start messing with both sides of the equation. We can't. We have to stay on one side of the equation. So here's where that algebraic rule on the right hand side I already mentioned I'm going to use. I'm going to multiply the top and bottom of this by the difference of perfect squares of that numerator. This is the binomial 1 plus sine x. And so I'll multiply the bottom by 2, 1 minus sine x. So multiplying by a value of 1 is not changing a fraction. The top would then become 1 minus sine squared x over, the bottom stays 1 minus sine x times cosine x. So 1 minus sine squared x, we're going to Pythagorean identity, that's going to equal cosine squared x. So we get cosine squared x over 1 minus sine x times cosine x. So now I have this cosine squared x on top and a cosine x on bottom, so that cosine x on the bottom is going to reduce out with one of these on top. So then we get cosine x over 1 minus sine x, which is what we're needing to get to. Now, if it was me, my personal preference, I would multiply the right-hand side by 1 plus sine x over 1 plus sine x right away, and then I would try breaking that back apart into two fractions. I feel that it tends to be a little quicker when I deal with that difference per squares right away, but it works out either way. Here's one more. We have the left side and the right side equals 1, so I would probably deal with the left-hand side here to kind of give me a starting point. I would change them into some of the similar or same functions. So cosine x times cosecant is 1 over sine x, and then tangent is sine x over cosine x. And then the sines reduce, the cosines reduce, so you get 1 equals 1. It's actually a simple one once you change these into the equivalent reciprocal or quotient groups. Now when I see the 1 minus sine x here, that's going to be equal to cosine squared x. Cosecant squared x I can change into the reciprocal, 1 over sine squared x, so 1 times cosine squared x. So I can write this as 1 fraction cosine squared x over sine squared x. And that itself is an identity. Cosine over sine is cotangent. So cosine squared over sine squared will be cotangent squared x. So those are just using trig identities, not much algebra. So we're going to call it good. A few examples. It's tough because there's not a process or a step-by-step instruction book that can give you these. A lot of it's using your identities and algebra skills to manipulate these to find the equivalency. So a little bit of a puzzle. You have some good background knowledge of algebra along with these trig identities. Have those out if you need them, but try to be able to pull those out or see them within the problem and not be reliant upon always looking for those within a textbook. See you tomorrow.